Welcome back, everyone. We're going to continue right where we left off last time, and in part 2 we're going to focus on actually reading in our data. We'll do a quick visualization of the data, and then we will set up our data with the data loader, as well as do a train test split. Let's get started. Okay, here's the notebook as we left off last time. We have some imports. We created our model class object, and then we made an instance of our model class. Next, what we're going to do is just explore the data set. We'll first use pandas, so I'll say import pandas as PD, and we'll also be visualizing the dataset a little bit, so I'm going to import matplotlib as well. So to do this, we'll say import matplotlib.pyplot as PLT, and depending on what version of Jupyter Notebook you're using, you may need to also say matplotlib inline. Keep in mind this inline command, that's only for notebooks. If you're running this as a .py script, you don't need this inline command. So I'm going to go ahead and run those imports, and then I'll read in the data set. We'll say df is equal to pd dot read CSV, and then I'm going to read in from our data folder the iris data set. You should be able to always tab autocomplete this. If you are not able to tab autocomplete this, it means you're looking in the wrong directory, so go ahead and provide the full file path. So there's our data frame. Let's go ahead and just check out the head of it. So here are our measurements. We have sepal length, sepal width, petal length, and petal width in centimeters. And then this target, that is actually the target class, and it's going to be a 0, 1, or 2. So 0 goes with iris setosa, 1 goes with iris virginica, and then 2 goes with iris versicolor. So if I check out the tail end of the data frame, you'll notice this data is essentially sorted by the class. So it starts off all the zeros, then in the middle are all the ones, and then towards the end are the twos. Next what we're going to do is we're going to plot out the data set just so you can get a feel for it. Now this is just kind of a complex plot, so I'm going to copy and paste the code underneath plot dataset from our notebook. You don't need to worry about memorizing this code. It's essentially just showing you how we can explore this data set. So this is more just for the visualization. Again, I'm just copying and pasting this from the lecture notebook that goes with this lecture. Go ahead and run this. Make sure you've already imported matplotlib in order for this to work. But once you've done this, you should see this plot show up. So essentially what this shows is we have 3 classes here, iris setosa, virginica, and versicolor, and then we're plotting them in a 4x4 with petal width versus petal length, and then petal width versus sepal length versus petal length, and then sepal length versus sepal width. And we can get an idea here that iris setosa should probably be easier to classify than iris virginica and iris versicolor, because you'll notice these blue points tend to be more easily separated than the other 2 classes. But often you'll see that if you are able to utilize the information across these 4 features, you should get pretty good separation between all 3 classes. And hopefully our network is going to be able to do that. So what we're going to do now is perform a train test split. So I'm going to say x is equal to, and we'll say df drop, and I'm going to remove that target. And because it's a column, I need to say axis is equal to 1. And the next thing I'm going to do is say y is equal to, and then I'm just going to grab the target column. And for both of these, what I'm going to do after I grab them, you'll notice x is still a pandas data frame, and y is a pandas series. So if I check the type of y, it's a pandas series. In order to convert these into float tensors without any errors, I'll go ahead and just convert them into NumPy arrays. So we'll say x dot values, and we'll say y is equal to y dot values. And now if you check out x, it's that NumPy array. So same information, just encoded as a NumPy array. So let's go ahead and perform our train test split. In order to do that, we'll need to import it from scikit-learn. We'll say from sklearn.model-selection import train test split. Go ahead and run that and import it, and then call train test split. So after you've imported this in the cell above and you've already ran that cell, you should be able to do Shift Tab here inside Jupyter, expand this little auto help, and then scroll down until you see the example here where it kind of passes in xtrain, xtest, ytrain, and ytest. So I'm going to grab these just to save myself a little bit of typing. So this makes sense. Our train test split should return back these 4 items. And then what we're going to do is just pass in our x and y. We need to choose a test size. I'll go ahead and choose a test size of, let's say, 20%. And my random state, make sure you choose the same random state I do, otherwise your split will be different than mine. I'll choose a random state of 33. So train test split will also shuffle our data, so we don't need to worry about the fact that our data was in order here. Next what we're going to do is to go ahead and convert these into float tensors. So we'll say xtrain is equal to, and here we're going to call torch, float tensor, and just pass in xtrain. And we're going to be using this essentially for the x test as well, so we'll copy this, and we'll say x test is equal to float tensor of x test. So that takes care of the features. Now something we mentioned previously is when we're working with multi-class classification, we actually want to one-hot encode our labels or that target value. However, with PyTorch, if you use the cross-entropy loss, which we are going to do later on, you actually don't need to do that step. So I want you to keep that in mind, especially when we actually import the cross-entropy loss. So for convenience, I just need to say ytrain is equal to torch, and I'm going to make this a long tensor because it doesn't need to be a float. It doesn't need to be 0.0, 1.0, and 2.0. They just need to be 0, 1, and 2 since they're just labels or categories. So we'll say ytrain is equal to torch.long tensor of ytrain, and we'll do the same for ytest. We'll make it a long tensor of ytest. Finally, let's go ahead and finish off defining our model. So what we're going to do now is we'll say that the criterion of our model is equal to nn.cross entropy loss. And this is essentially how we're actually going to measure our error. So the criterion is what is the criteria you're using in order to measure how far off your predictions are from your data. So recall we're going to be first training on xtrain, which means our predicted values will be compared to our ytrain values. And then later on we'll use xtest and ytest to evaluate on data that the model's never seen before. So that's our criterion. We're using cross entropy because this is a multi-class classification problem. And then we need to choose our optimizer. So we'll say optimizer is equal to torch.optim atom, and then we'll say model.parameters, and then we'll set our learning rate. So that's LR, and we'll set it to 0.01. So let's go through and what this is actually doing. So as you can recall from the theory lectures, we have a wide variety of optimizers to choose, and one of the most efficient ones to choose is atom, so we'll choose that here. And then we pass in the model parameters as a generator. So if you just call model parameters, open and close parentheses, and run that, it's a generator object that actually returns the parameters of the model. So if you call it just as an attribute off that model object, this is essentially the parameters of the model, which in turn are the layers of the model. So there's the fully connected 1 layer, fully connected 2, and then the output. And we can see how they're all connected here. So we're essentially generating that or feeding these in to the optimizer. And then we have our learning rate. And the learning rate is something you can play around with. If you feel like the error or your loss is not ever really going down after training for a lot of epochs, you may want to decrease the learning rate and see if that helps. So something like a decrease would be 0.001. So I would recommend starting off at 0.01 and then decreasing if you're getting that issue of even after something like 10 epochs, your error is not actually going down. Okay, keep in mind there's always a trade-off that the lower the learning rate, the longer it takes to train your data, or your network, I should say. Let's now go ahead and train our model. So we have to do a couple things. First, we have to decide how many epochs are we going to train for. So the number of epochs, and this can be a bit tricky to choose at first, especially if it's an unknown data set. So what I would recommend is starting small on your epochs if you're doing for a large data set, and then later on plot the loss function, which we'll show you how to do in just a second, and then decide if you need to train for more epochs. And you may be wondering, again, what is an epoch? An epoch is one run through all the training data. So seeing all the training data one time. So I will go ahead and say epochs is equal to 100 here. And the other thing I'm going to do is I'm going to set an empty list in order to append my losses to it. That way I can keep track of my losses. So what I'll do here is say for I in range epochs. So essentially for every epoch, what I need to do is I need to actually run forward through my network and get a prediction. So how do I do that? It's actually pretty easy. We just say our predicted value is going to be equal to model, and we call that forward method. And we have to pass in the x. So what is that x data? For our training set, it's going to be x train. So if we scroll back up here and we take a look again at our model, forward here is just at first passing in that x, which we then pass into that full network, pass into the activation function, then the result of that gets passed into the next layer, into the next activation, and so on, all the way until you get its output. So that's essentially what we're doing here, where the very first x is the training data. So that goes forward through all the layers in the model, and then we get our predicted result. You can imagine the very first time you run this, the prediction is going to be really bad, so you should have a high loss. But we should actually measure that loss. So let's go ahead and calculate the loss. So we're going to calculate our loss, or error. And how do we do that? Well, we already have cross entropy loss as our method here as criterion. So this allows us to simply say loss is equal to criterion, and then we pass in our predicted values against y train. And because we use cross entropy loss, we don't need to do any one-hot encoding between ypred and y train. Next, we want to go ahead and keep track of that, and we'll say losses, and we will append that loss here. Okay, so we went ahead forward and got the prediction, calculated the loss error, and then kept track of it. Let's go ahead and print this out for the user. So we'll say, let's print it out every 10 times. We'll say if I mod 10 is equal to 0, go ahead and print out, and it's up to you how many epochs you want to print out for, but we'll kind of print out for every 10th one. We'll say epoch that we're on is I, and loss is, and then we'll go ahead and print out the current loss. Let's go ahead and make that capitalized. So essentially this is using print formatting or string interpolation so that when I is immediately divisible by 10, we'll go ahead and print out the epoch we're on and the loss we're on. Okay, so we should start seeing that printed after 10 epochs. And then what we're going to do is perform backpropagation at the end of this. So what do? We take our optimizer and we call 0_grad. So essentially finding where the gradient is 0. So recall we're looking for minimums there. And then we move backwards for backpropagation. We do that off the loss function. And then we say optimizer.step. So essentially these 3 lines of code, this is your backpropagation process. So you can see here how PyTorch really simplifies that for us. And then once we're done with that, we can go ahead and run it. So we have the desired number of epochs. This is technically not necessary, but I would encourage you to keep track of your losses per epoch, that we can plot it out and analyze it later. Then for every epoch, we'll go ahead and pass in the training data, put it forward, then calculate the loss, keep track of that loss, print out a report while it's training, and then for backpropagation, we run these 3 lines. Let's go ahead and run that, and it shouldn't take too long, but you can see here our beginning loss is 1.15, then it begins to drop down, and so on. And now we want to answer the question, well, was 100 epochs enough? A good way of noting that is by plotting out the epochs versus the loss. So we can say plt plot, and I'll say for a range of epochs, go ahead and plot out the losses there. And let's give this some labels before we plot it out. So the Y label, that's just the total loss, essentially your error. And then your X label, that's going to be the epoch you were on. So when we plot this out, and this is essentially the behavior you should be seeing when you're training your neural networks, is at first you get a pretty good decrease in loss. So your error is going down, down, down as you keep training on more and more data. But eventually what's going to happen is you're going to start converging after a certain number of epochs to some sort of minimum loss. And in this case, we're actually pretty close to 0, but realistically, and depending on your data, you may not ever reach 0. It may start to converge maybe here around 0.8 or something else. But the idea being is once you start converging on your training set to some sort of loss value or error value, you've probably trained for enough epochs. So you can see here, somewhere between 80 and 100 epochs, we're really starting to converge. And technically, we're still going down, and we could have trained for more epochs, but It really depends on the situation if you want to train more. If each additional epoch is maybe a whole day of training because you're dealing with a huge complex data set, that may not be worth it for a drop in 0.01 loss. But if it just takes, a couple of microseconds, you might as well train for more epochs. Okay, so coming up next, what we're going to do is in part 3, we will validate the model, save the trained model to a file, and then load it up, and then we'll apply the model to classify totally new unseen data. I'll see you there.